Okay, started. Great. Welcome to Circus Research Webinar Series and TGIF. Today we are ending the old flood presentations with a new one, GIS modeling of urban flood-prone areas. I have with me Circus data analyst and GIS specialist Katerina Masida. Her research focuses on climate adaptation and resilience, and she specializes, oh my God, Friday, right, in environmental and marine science and technology. Before we give the floor to Ms. Masida, just to give you a reminder on the webinar logistics that you can type your questions anytime to chat box or Q&A, and then we'll try to answer them at the end of her presentation. Thank you so much, and Katerina Masida, we are ready to listen to you.
Thank you, Dr. Gabriel, for the nice presentation. So I'm going to show you some GIS modeling of urban flood-prone areas, and we are going to focus on the New Haven Harbor area. New Haven Harbor is one of the largest flood-prone areas in the Connecticut coastal line. Our first goal is to simulate different scenarios using FUNWAVE model and merge the result with OpenStreetMap shapefile to study building and street, and geocoded shapefile to study lifelines, to understand what features are going to be affected by different extreme flood events. The second goal is to simulate the same extreme flood event with and without flood control structure using the model at sea, and analyze how the number of affected roads and buildings is going to change. So to simulate for different flood event scenario, we use the nearshore model FUNWAVE. The main goal of this project is to better understand how the New Haven Harbor community is going to be affected by different flooding scenarios. To study, analyze for different scenarios with a return period of 10 years plus 20 inches, that is the sea level rise projection for 2050, 100 here and 100 here plus 20 inches, that is how an extreme flood event can be in 2050. For each scenario, we will show which road buildings and lifelines are going to be flooded, and the flood severity for each feature. So on our left, we have the sea level rise scenario in 2050. So we can see that the New Haven Harbor area will be affected, and an extreme flood event in 2050 would look like the right map. So we were able to see which roads are going to be affected, and using this flood fact sheet that we found on the Pennsylvania DOT, we decided to classify a safe street that we will get 0 to 0.5 feet, unsafe 0.5 feet to 1, flooding vehicles with water between 1 and 2 feet, and where the vehicle will be carried away if the street will get more than 2 feet. So here is the possible scenario in 2050, how we can see a lot of streets will be underwater, mainly the red ones. So here we we can see that the total number of miles that will be underwater in 2050 is more than 60. And in an extreme flood event, we will have more than 100 miles underwater. I want to underline here that with strict, we consider everything: highway, primary, secondary service that are parking mainly, sidewalks, part. So it's a huge amount of stuff, not just street. And here we did the same study, but for the building. So here we have a focus on the West Haven area, and on our left, we have all the buildings that are going to be affected in 2050. As we can, it's so, and here we have all the buildings in the New Haven Harbor area that are going to be affected. So in 2050, more than 1,000 buildings are going to be flooded, and in an extreme flood event, more than 2,000 buildings are going to be affected. So here we did a study on the airport, and here is the same map that I showed before, but with zoom on airport area. And in 2050, all the airport is going to be affected. So here we did a classification of the operational area, and in 2050, everything is going to be underwater. So here we have estimation of the square feet flooded in 2050, and in an extreme event in 2050. So another important things are the lifelines. A lifelines enables the continuous operation of government function and critical business, and is essential to human health and safety or economic security. So in 2050, a lot of lifelines are going to be affected, and airport, daycare, electric station, ferry station, fire station, food, and with food we mean supermarket, grocery, fast food, restaurant, everything that can provide food to the community, food processing, gas station, and pharmacy. Increasing the severity of the flood event, the number of features affected cases. Simulation with return period of 10 years plus 20 inches, which represent the sea level rise projection for 2050, show destructive results. Different action can be taken in order to protect the New Haven Harbor area. The following slides give an an idea how the Tweed Airport area can be partially preserved. And to do the second study, we use the ADCIRC model. The aim of this study is to show the different impact on the community that a flood event could have implementing or not implementing a flood control structure. In the simulation, we used peak water level during Hurricane Sandy, 2.6 meters. 3 different possible scenarios were analyzed. So we are going to call case 0 our current situation, not flood control structure. Case 1, flood control structure implemented across Morris Creek and Far River. And case 2, flood control structure implemented across Morris Creek, Farm River, and Morris Cove. An estimation of the miles and type of street flooded was computed, as well as the number of buildings flooded. So in the area that we are going to study, the type of streets that are involved are secondary, tertiary, residential, service, footway, path, and track. So this is our case 0, and we decide to use the Hurricane Sandy because he has a return time between 40 and 100 here, and based on our study, 100 here is pretty close to 100 here plus 20 inches. So that could be what is going to happen in 2050 if no action are going to be taken. So in this scenario, there will be 22 miles of street flooded, mainly service, primary, and footway. This is case 1, where we put a flood control structure on Morris Creek and Farm River, here and here. So the extent of the flood is not really dropping. And in blue, we see the streets flooded, and in purple, the buildings that are going to be flooded. So now the miles flooded are almost 19, and still service, primary, and footway are the most impact. And this is case 2, where we put a flood control structure on Morris Creek, Farm River, and Morris Cove. These 2 small ones. Okay. So, and here we can see that the extent of the flooding is much smaller. Unfortunately, as we can see here, the miles of street flooded is not really dropping down, but our conclusion was that the main flood is coming from here, from Morris Cove. So here, we still have service, footway, and primary. So yeah, in case 0, we have 649 buildings affected, and using the case 2, only 156 buildings are going to be flooded. So the result of the study shows that the implementation of a flood control structure could help New Haven Airport area in cushioning a flood event. implementing case 1, there would be
I'm gonna pull the slides. Just a second, everybody.
I don't know what happened. Sorry.
That happens. Technical problems. Just 1 second. Share. Done. Sorry about that.
What was the last one?
Can you see the slides?
Yeah, but was the last? Yeah, this one.
Okay.
So this one is with the building, and the last one was with the final result.
This one?
Yeah. So where did I stop?
It stopped in when you were explaining here the previous graph.
So implementing case 1, there will be 25% less of buildings flooded and 13.4 less of roads flooded. Implementing case 2, there will be a 66 decreasing of flooded building and decreasing of almost 20% of road flooded. And this is the end of my presentation. If you have any.
Thank you so much.
Sorry for the.
Oh, thanks so much, Katerina. That was great. So now I'm going to keep sharing the slides and see like what are the questions, and then the chat box from everybody. Just a second. Okay, now we're getting some questions. The slides and the video will be available to view to all the participants and registrants later on. So the first question that we have is like, when you are doing the GIS modeling, what kind of elevation data or topographic data that you used?
So to run both model FUNWAVE and AdCirc, we decide to use CONED because it's much better for the bathymetry and is good enough for the land. Instead, LiDAR is very good for the land, but is like very bad for the bathymetry. So because we are simulating a flood event, we decide to have a better bathymetry and a better resolution for the model.
Another question that we have is like, what are some of the common challenges that you have facing with GIS modeling of the flood projections?
So one problem is that CONED and LiDAR, they don't take in consideration the elevation of bridges. So in the beginning, we have like very bizarre results. So that's why we look for OpenStreetMap, because the shape file of the street have like option to select or unselect bridges. And so what we did, all the classification for the streets, they don't consider bridges because they are not on the LiDAR, when we were computing the amount of water over the bridge wasn't the real amount of water over the bridge, but was the amount of water from the bottom of the river or channel or harbor. So was totally wrong. I don't know if this was too technical.
Ms. Masida, if you want to elaborate a little bit about like the accuracy of the GIS model, the estimation of the flood depths on the roads and the buildings, how confident that we are on the results and which regions that needs like further evaluation?
So our model, can be run almost everywhere in Connecticut. The output of the model, of the FUNWAVE model, is pretty good, is 1 meter by 2 meters almost. And but this is this, and so we are able to compute the amount of water above the land only with FUNWAVE, because the output is a raster, and our postdoc Cheng Liu was able to do it with the model. Unfortunately, with the other one, AdCirc, we don't have as output a raster, but it's a point shape file, and the points are not close enough and well distributed to just use a function point to raster or something similar, because was really weird, was a bunch of points just in a line, and in the middle was empty. And so for that one, it's not really possible to compute the elevation of water. We are pretty confident that what we got as result for the street building has a good.
Thank you. This one is about the female lifelines. Is there like a data set that we can download all the defined female lifelines? I'm going to the slide that describes the female lifelines here.
So that was a huge challenge that we went through also for another project, the CPI. That, and so basically what we did, I went to the connecticut.gov, and there is like a huge website where you can download an Excel file for every lifelines, basically. So if they have a license to sell food, it's like you can download the address, and using ArcGIS online, we were able to have a point shape file, but so far there is not really a website where you go and say, oh, I want to see where all this lifeline is possible for a hospital, school, because our and if I remember well, was the Department of Housing, and but not for like other stuff. So what we have here, like gas station, it was a long process from an Excel file with the license and the address to geocoded file, shape file. If someone knows that there is a Lifelines website where it's possible to download everything, we would love to.
That's true. The next question is about the airport area. So I will go to those slides. They were asking about like what are the dimensions of the flood control structures, and so I think there was like, and then the locations of it. So can you please repeat one more time the differences between case 0, case 1, and case 2?
So in case 0, we don't have any flood control structure. For my understanding, there is something here. There is something in Morris Creek, probably, but it's not big enough. And in case 1, there is one in Morris Creek and Farm River, and they should be 2 meters by 5 meters. And in case 3, there is Morris Creek, Farm River, and Morris Cove. And for our understanding, the more effective one is Morris Cove, because it's the one that can stop the airport, that can stop the flood to reach the airport. But to make sure that we are planning to do another simulation with Morris Cove and Farm River without Morris Creek, probably, and see what is going on. Our guess is that it's not really going to change from case 2, but we want to make 100% sure of this.
Mm-hmm. I'm taking another look on the chat and the Q&A, and seems like these are all the questions. Thank you so much for listening to us, and I'm going to share now and update you about like our next presentation. Ms. Masida, thank you so much for your presentation.
Thank you.
And if you would like to learn more about Ms. Masida's like the results, you can come here to our registration website and check our project fact sheet. The presentation will be available also on our YouTube channel soon, and you will get notified as an email. Since we finished all our flood presentations so far, we have a different subjects to explore on our last week of research webinars. Next Monday, that we are going to talk with Professor Mariana Fragomeni in the change in heat vulnerability and land use influence. Please join us, and you can register us to that presentation from Register Today website. Thank you for joining us, and see you next week.